Good morning, everyone. Today we're going to learn how to test means. So we already did a little bit of that in the previous video. We tested two different means to illustrate how, we tested a single mean to illustrate how hypothesis testing works. So the first thing we're going to learn how to do is test means when we don't know what the population standard deviation is, because that's almost always the case. We almost always have to estimate the population standard deviation, and consequently we almost always use something like a t-test to determine if means are different. Okay. So what I want to do is I want to go back to the example we had in the previous video and then show you guys how it would change if we didn't know what the population standard deviation is. So you've already dealt with this a little bit when we were generating confidence intervals, so hopefully this won't seem too new to you. All right. So first I want to look at how we calculated the standard error and show you one thing you have seen before. So you may remember when we were working with the difference between two means, we used that formula to generate the standard error. Now I'm going to make a couple of rearrangements. Notice that if I add the numerators together and divide by 2 and then multiply 2, see how those would cancel out, so I haven't really changed anything? As long as n is the same, then it's going to be in the denominator. And you have seen that formula before. So MSE stands for mean squares error. This is something that Lane frequently uses. All right? So essentially the idea behind this is we average the variances. That's what the mean squares error is. If you look at this, if you only have two variances, and you add them together and divide by 2, you're averaging them. Now in this chapter 12, we'll be doing a lot of averaging of variances, because we're going to start out just comparing two means, but later we'll be comparing multiple means using something called the Tukey test. As you're going to see, the Tukey test also contains a mean squares error. And you see it in other statistical tests like analysis of variance, which is something we don't do in this class. But if you go on in science, you're probably going to be doing analysis of variance at some point. Okay, so I just wanted to show you where that particular formula came from. Now, you may remember in the previous example, we had a difference between means of 2. So we had the fertilized plants and the unfertilized plants. We subtracted them from one another. We had a difference of 2, all right? And then we also had a hypothesized value of 0. That was the null hypothesis. So we had 0 because if there's no difference, then we expect the difference between means to be about 0. Okay. We also calculated a standard error. This was working with n equals 20 for both groups. I'll add that up here. All right, so we had two different groups. We had fertilized and unfertilized plants. Just to make it simple, we had the same sample size for both. And you may remember that I told you the population standard deviation was 4. So we plugged all this information into this formula. We came out with a standard error of square root of 1.6. Okay. All right, so now what we're going to do is move over to this next little panel I've set up here. All right. So we found the probability of getting 2 by modeling the null hypothesis. Remember that? So that was familiar to you. We generated a normal distribution. We put 0 as the mean of that distribution. We looked to see where 2 was, and we used the standard error as the standard deviation of that distribution. So that's very familiar to you. there's another way to do it, which again is something you've seen before. So you remember this. So this little formula essentially takes the normal distribution we were working with and changes it into a standard normal distribution. All right? So that's what a standard normal distribution would look like. So remember, a standard normal distribution has a mean of 0 and a standard deviation of 1. So this is equivalent to the normal distribution we generated before. So before, remember we were looking where 2 was, and we found the probability of getting 2 or more. Now what we need is we need to find a value here that is equivalent to 2. And that's what we use that formula for. So I'm going to change it a little bit here because we're going to be using this more often when we're calculating t-statistics. What we would be putting in to find out where 2 is the statistic we actually calculated. So that was the difference between means, the 2 there. Remember, we subtracted the 2 means and got 2. And then minus the hypothesized value, which was 0. That was our null hypothesis. And then the standard deviation of, that we're trying to convert from had standard error in this position, right? Okay, so to get that score, to get this score that is equivalent to 2, that's what this z-score is. What we do is we take 2 minus 0, so that's the statistic we calculated. In this case, it was the difference between means. We subtract 0, that's the null hypothesis, and we divide by the standard error. Okay, so that gives us a z-score. Now, you can model this using Lane's calculator. All right, let me be sure everybody can see this. So you can make a model of this using Lane's calculator. We just did this in the previous example, so I'm assuming you know how to do this. So you want to, it's kind of the default is a standard normal distribution. So it should have a mean of 0, a standard deviation of 1. When you place the z-score on there and look for the value above, you get the exact same probability we got working this a different way in the previous example. Okay? Now, how do you report this? All right. So we're going to come down here. Let me just make sure it's all visible to people. Okay. So last time we wrote a sentence like this. We did not find a difference between the fertilized and unfertilized plants. Remember, for a two-tailed test, we would be comparing that probability to 0.025, right? If it's a one-tailed test, you'd be comparing that probability to 0.05, all right? So we failed to reject the null hypothesis. You don't want to say that because it sounds like jargon and people don't know what you're talking about. Instead, this is what you would say. We failed to find a difference. Okay. But remember, we want to tell people what the probability is because they can look at that and go, well, that's a pretty low probability. Maybe if I redid this experiment with a larger sample size, I might find a difference. Okay. I also mentioned that usually you want to report a statistic and a probability. Well, last time we didn't actually calculate the statistic that is ordinarily reported. This time we got it. That's the z statistic there that we calculated. So the way you usually write this is you write little z here, and you put the sample sizes of the two means, okay, as subscripts. So remember we had 20 fertilized plants and 20 unfertilized plants. That's the z statistic that you would get. And then this is the probability that we found by modeling this using Lane's calculator. Okay, why do we do it like this? All right, the reason why is this is the way things have been done traditionally. So before we had calculators like Lane provided, nobody could model this directly without a whole lot of work. So normally you would use the formula we were just looking at to calculate a score like this, and then you would go to a table, right, with all the sample sizes and the z-scores, and you would look up what the probability is. So that's one reason why people report this information this way. Okay, so what we're going to do now is we're going to go through the same procedure, but we're going to see how we would do this if we didn't know what the population standard deviation is. So I'm actually going to go back over there to the other end of the board and change things to show you what would change. All right. One big thing is, instead of having a z statistic here, we're going to have a t statistic. And you probably remember that for Lane's calculators for t statistics, they don't make a nice graph for us to look at. Instead, what we do is we put in degrees of freedom and out pops a probability value. That's another reason why we have to work this a different way, using that conversion to the standard normal. Except now we're going to use that same formula to find t statistics. Okay, so let's go back to the other end of the board. All right. Hold on just a minute. Reposition everything here. Okay, so let's change a couple of things. All right, so this is the main thing that's not going to be true anymore. So we don't know what the population standard deviation is. If you don't know what the population standard deviation is, you use a t statistic. If you do know, you always use the procedure we've done before. You use a normal distribution, you calculate a z statistic. So that's the first thing you want to ask yourself if you're looking at a problem in Chapter 12. Does it have the population standard deviation? Okay? Now, remember things like correlation coefficients? Those work with that Fisher's Z distributions. For those, you know what the population standard deviation is, even if it's not given in the problem, you know. It's assumed that you know that. And then it's also true for proportions, because those are approximations of this. So for both of those situations, you do work with z statistics instead of t statistics. Okay, but let's get back to this, all right? So let's assume nothing has really changed. So we still have 20 plants of each type. When we subtract the means, all right, so let's do mean of the fertilized minus mean of the unfertilized. We still get 2. Okay, so all that's the same. What we're going to change is, let's change the variances. So usually what we would do is we'd take our 20 plants from the fertilized plot and we would find a standard deviation. So let's say we do that and we get 3.5. All right, now then we take our plants from the unfertilized plot and we calculate a standard deviation of those. All right, so we'll use SU for the standard deviation of the unfertilized plots. Let's say we do that and we get a higher number, 4.5. Okay, now here's an important thing. An assumption of a t statistic is that the population standard deviations are equal. Got that? Now the key thing there is population standard deviations. Notice these sample standard deviations are different, but the assumption is that they are the same. All right, this is one of the reasons why we average the two variances to calculate the standard error. Now, looking at that, you can probably see that when we average those two, it's going to be 4. I did that on purpose because that way, you know, when you can plug it all in. You're going to get the same thing we had before. So I'm going to keep this the same just so we don't have to redo everything over here. All right, but this is why this is called mean squares error. It is called that because it's an assumption of a t-test. It's not an assumption when you're working with the z-statistic, even though you still average them. But they are usually the same if you're working with the z-statistic, or they should be the same. Okay, all right, so it's an assumption of a t-test. All right, now let's go over here to the next thing. All right. Okay, how does this change? Well, it doesn't change. So isn't that nice? That makes that nice and easy. But instead of getting a t-statistic by going through this calculation, a z-statistic, you get a t-statistic. So notice the answer exactly the same. So same procedure. You put in the statistic that we calculated, 0. The hypothesized, 2. The hypothesized value, remember that's the null hypothesis. I notice this is sort of wrong here. This should have been UF minus U equals that. Okay. All right, let's see here. Okay, so that's the t-statistic. All right, now, what next? How do you find it? All right, well, let's look at what we're going to be doing. So that's the standard normal distribution, right? Okay. What we're going to be doing, though, is we're going to be working with a t-distribution. So the process is essentially the same. The thing is that a t-distribution is a little more pointy. I made that a lot more pointy, but it's actually not like that. Okay? And a little more spread out. So this shape is called leptokurtic. All right? So it's a deviation from normal, but that's the shape of the t-distribution. So it has this leptokurtic distribution. What that means, if you look over here, notice that there's this tail here. That's going to make the area larger. So the p-value we get for this t-statistic is going to be larger than the p-value you get using the normal distribution. All right? So like I said, all this is going to be essentially, the same. Okay, now to find this, though, to find this probability, we don't model the t-distribution directly. By the way, its shape changes dramatically depending on your sample size. So it becomes like more leptokurtic when you have smaller sample sizes and closer to normal when you have larger sample sizes. This may be one of the reasons why Lane doesn't provide some kind of graphic version of it. Okay, what we need to find the t-statistic are the degrees of freedom. Okay. Now, you have calculated degrees of freedom before, so you probably remember we lose a degree of freedom for each variance that we estimate, okay? Or each standard deviation that we estimate, if you want to call it that. Remember, for this example, we had 2 standard deviations we were working with. So we had one that we estimated from our fertilized plants, and one that we estimated from our unfertilized plants. We had 40 plants total, but we lose 2 degrees of freedom, okay? So you may remember a formula that looks kind of like this, N1 minus 1 plus N2 minus 1. So these are our 2 groups, you see what I mean? That's one way to do it, so you have basically the 40 plants in this example, you lose 2 degrees of freedom, so that leaves us with 38 degrees of freedom. Okay, so that's a pretty large number of degrees of freedom. All right, now what we're going to do is we're going to go to Lane's calculator for this. So I'm going to move the camera over here and show you this on this screen. If you guys will just give me a minute. Let me probably have to log in again. Okay, let's see. Okay, so that's pretty clear. All right, so first what we do is we put in the t-statistic that we calculated. Now let's see. So I had originally done I kept all the decimal points, but I'm just going to put in what I had on the board. So 1.581. All right, that's the t-statistic we calculated. Now we need the degrees of freedom. Okay, so we'll put that in. All right, so that's 38. All right, and then you hit calculate, and there's the probability. So as you can see, the probability is even higher than it was using a normal distribution. All right, and that's just because there's inherently more uncertainty when you're working with samples where you don't know what the population standard deviation is. Okay, so how do we report this result? Notice that that is for a two-tailed test because that is almost always what we'll be doing. Okay? All right, so I'm going to go back to the results statement to show you what would change. Okay. So here we have our results statement. So essentially we would draw the same conclusion because we compared that value of 0.1222 to 5%. It is much greater than 5%. So we didn't really find a difference. So what we would put, instead of putting a z-statistic, we put our t-statistic. So 20, 20. Remember, this was exactly the same because, I did this to where the standard error was the same. Notice you calculate the standard error the same way in both the examples. All right, so this is 1.581. All right, again, we're reporting our sample sizes here. And then we put P equals the new probability, which was 0.122, I think. Let's see if that's what it said. Yes, that's right. And for this, I've rounded off to 3 decimal points because that's what I usually ask you guys to do on quizzes and tests. Okay, so I will stop this recording here and make room for another part of this chapter.